Hey, what's up? We should fix some mistakes, shall we? So in last week's video, if you haven't seen it, I will leave a link in the description. We looked at somebody comparing a logistic regression to a neural network. And I wouldn't say they did terrible, but they did bad. So now I'm going to reanalyze things the way that I would do it. And specifically, I'm going to compare 3 different techniques. One is VSURF, which I've talked about before. 2 is my method for variable selection, which I'll leave a link to the video that compares those 2. And the third one, which I haven't talked about at all on this channel, is Lasso. So we are getting our cowboy on in this one, baby. So yeah, as a reminder, in the original data set, they had 216 stroke victims, and they're trying to predict those who would have a positive stroke outcome measured using the Barthel index. And they took a continuous variable and categorized it. So the first thing I'm going to do is I'm going to leave it non-categorized because that's the better way of doing it. And they also found that logistic regression kind of sucked because they were using stepwise, which of course it sucks because stepwise is terrible. And they also found that neural networks do better than logistic regression. And I had a lot of problems with the way they did things. And I will again link that video down below if you want to see it. Instead, we're going to look at what I did. So we're going to go ahead and step into R now. All right, we have made it into R. Now I'm going to require flexplot, tidyverse, and the party package for random forest. I should also require VSURF. I do that later, but I like things being neat and organized. Then we're going to read in the data. And just to give you a view of it, we'll go ahead, train for training data. And we've got all these biomarkers related to health and stuff like that. The primary outcome of interest is going to be Bathel.follow.up. Notice they spell it Bathel here and Barthel here. Don't know why. Probably a mistake. But first thing I'm going to do is I'm going to use my approach that I've talked about in a couple of videos and I've mentioned in a paper, and I will link that paper in the description. What I'm going to do is I'm going to use random forest, and that's going to give me a variable importance for all the variables. It also gives some other things. So we got a model R squared. We're explaining 52% of the variance, and most important predictor is Barthel, the baseline Barthel score, and then following that it's nihs, and then HB, et cetera, et cetera. So then the second step of what I'm going to do, and again, let me put this all on one line or on 2 lines so you can see it all. If you need a review of the strategy I'm using, I will link that below. But what I'm going to do is I'm going to take the top 4 variables. Why the top 4? Because that's all that FlexPlot can visualize, and we are going to hope and pray that 4 is enough. Or in other words, there's no variables with signal beyond 4 variables. And then I'm going to start by just looking at the bivariate plots. And so, not surprisingly at all, your baseline Barthel score is going to be highly correlated with your follow-up Barthel score. And I don't remember the amount of time span between these 2 things, but whatever. And if we look at the second most important variable, NHSS, that's a disappointment. It doesn't seem to be all that predictive, at least according to the random forest model. So I'm going to evaluate whether we can get rid of NIHSS. And the next is HB. And by the way, I don't know what any of these variables mean. But I will link the paper, so you can find out if you want to know. HB has a slight signal, at least in the middle range of HB. And then D.dimer. Dimer. It's like diner, but with an M. Yeah, that's cool. And so it looks like we might want to nix dimer and NIHSS. And put all these on 2 lines. So now what I want to do is I want to see whether there are any potential interaction effects between these variables. So I'm going to look at each of the variables with the most important predictor and just see if there's non-parallel lines. And so I've added ghost lines here that are gray, and it looks like those are definitely parallel. I mean, as parallel as a jagged line can be, but we don't have these huge deviations from parallel. So it doesn't look like NIHSS is interacting with Barthel. But what about HB? And same thing. You might be able to argue that in this left plot here, that maybe there's a weaker slope, but probably not. It's probably just noise. And then if I did that for D-dimer, Same thing. So looks like it is all just main effects. So that makes things much easier. So now what I'm going to do is I'm going to do a model comparison. And I like to visually align these things just so you can see the model comparison that we're actually doing. And I am trying to see what happens when I remove nihs, so fit a full and a reduced model, and then look at a visual comparison. And that's what we get. The full model is the red line. The reduced model is the bluish greenish line. And that's not all that impressive. That's too bad. So it looks like from this visual, like they're basically predicting the same thing. So it tells me that nihs really isn't adding anything. But let's go ahead and do a model comparison and get some numbers to back up our judgment. So AIC is favoring the reduced, BIC is favoring the reduced. And how you tell with both of these is the smaller the number is the preferred model. So both of these prefer the reduced model. Bayes factor is almost 13. So the evidence in favor of the reduced is 13 times stronger than the evidence in favor of the full. P-value is 0.942. R-squared is almost identical. And then adjusted R-squared favors the reduced. And predicted differences, on average, they're not predicting that much of a difference, and we saw that in plots anyway. So yes, we can definitely nix nihs. Now, let's see if we can get rid of dimer, because that's what we saw in the plot earlier, that it didn't seem to have much signal. So let's try fitting a full and reduced model with dimer. And we see that there is potential, maybe, because we definitely see different predictions, but it's only out here where there's not many data points. So it's maybe ambiguous. Let's go ahead and see what the statistics say. So AIC favors the reduced, BIC favors the reduced, and then Bayes factor favors the reduced, p-value favors the reduced, and R-squared, there's only 0.3% variance difference. Adjusted R-squared, very, very slightly favoring the full model, but not by much. So the evidence seems to suggest that we got a nix D dimer. So got to get rid of our dimer variable. So now that just leaves us with baseline Barthel and HB. And so if we were to fit that and then visualize that, I'm going to do a residual analysis. So by the way, this model... So before, they were doing a logistic regression, which was like needlessly complicated. You don't need to do that. You could just do a regular regression. And judging by these plots, it seems that the assumptions are basically met. So those residuals look nice and symmetrical. They're not perfect because you only got a sample size of 168 with the training set. There may be a slight bend in the middle, but not enough to worry about. SL plot, very slight heteroscedasticity, but again, not enough to worry about. So let's go ahead and look at the estimates and try to glean some information. So model R-squared is 0.6, so we're explaining 60% of the variance. And semi-partial baseline Barthel is explaining about 58% of the variance, and then HB is explaining about 2% of the variance. That's their unique contribution for the two of those. And then we got an intercept that we probably don't care about, baseline Barthel score. So every 1 point increase on baseline Barthel, we expect a 0.7 increase on the follow-up Barthel score. And I assume, and these are the same scale, so a 1 point increase means a 0.73 increase. So it's kind of like, you can kind of interpret it like a standardized estimate, and sure enough, I mean, they're basically the same thing. And then 0.24, I'm not sure what HB even means, so I don't know that I could interpret that for you. But those are our estimates. Let's go ahead and look at the visual partitions. If you don't know what visual partitions are, again, I will leave a link to a video where I talk about visual partitions, but it's basically just a summary of the entire model. So we're going to look at the Barthel effect, and there is a very strong Barthel effect. Not surprisingly, you're measuring the same variable twice, before and after. Of course, they're going to be correlated. And then if we look at HB, we see also a positive relationship. It's just not as strong as the baseline Barthel. So that is my approach, and that is the final model that I would come to. Now let's go ahead and use the VSURF package, which I talked about in a video. Again, I will link that in the description. And this is using random forest and some sort of algorithm that actually takes a while, so I'm going to start running it. So in the background, it's creating lots and lots of random forests and then averaging them and then using some variable selection strategies to come up with an optimal set of predictors. And so this is just extracting the name of the variables because this package, in my humble opinion, is not well designed. That it's a weird way to extract the information. Now with VSURF, there's various stages of selection. There's like 3 levels of selection. And I chose to look at the most selective. So I just wanted the very best variables. But I could have chosen some other thing which would have given me more variables, but instead I'm going to go with that. So if I were to run this, that tells you which index number of the variable or variables that we end up keeping. And we only ended up keeping 1, and it's the 6th one, which happens to be baseline Barthel. And so that's just giving it a name. And so now, I don't know if this is like part of the VSURF package, but I want to now fit a model with that one variable. So I'm basically using, it's kind of a 2-stage thing that I'm using VSURF to select the variables. And then at the end of the day, once I figured out which variable that I want to select, then I'm using just a regular random forest model to build that model that I can then use to make predictions on the cross-validation set, which we'll do in a bit. And that's what we got. So that is VSURF. Let's go ahead and do some Lasso. And by the way, I have never actually done a Lasso regression before until this video. So I'm kind of a newbie to it. I understand the basic idea, and I'll just explain the basic idea real quick. So the basic idea behind Lasso is we know that when we fit a data set, inevitably it's going to fit both the signal and the noise. Or in other words, it's going to overfit every time. And so what Lasso regression does is it tries to basically decrease the signal. So it'll take the slope of the variable, let's say the original slope is 0.5, and it will downgrade it to saying 0.4, which is equivalent to saying the relationship between these two variables is weaker than it actually shows in this data set. So that's all Lasso regression is doing. And through that process, it can also like downweight certain predictors to be 0. And that's what we're going to do. We're going to ask Lasso to try to basically take all these variables and see which ones we can basically set their weight to 0. So now let's go ahead and do Lasso. So this is just creating a data matrix of X, of just the predictor variables, and then a vector of Y that just contains the outcome variable. And then this is actually doing the Lasso fit. Now with Lasso, you need to remember how I said that it is downweighting the strength of the slope. And in order to identify how strongly to downweight that, you need to basically perform a cross-validation. That's doing that internally within that training data set. And so that's what that CV fit object is doing. It's estimating different weights that they could apply and trying to find the best one. And that's where best lambda comes in. So that tells you the weight that we're using to penalize variables. And then we could use this to extract the coefficients. And this is a matrix showing which variables were actually selected. So everything with a dot says that wasn't important enough to include. And then these now contain the regression weights of the Lasso regression. So these aren't the actual regression weights that you would use with a regular regression. They are the down-weighted weights. And so now we can go selected variables, Lasso selected, and then now we have an object that tells us which variables were selected, which are baseline, Barthel, and HB, which shockingly was exactly the same variables that I selected using my variable selection procedure. And now that we've done that, let's go ahead and compare the 3 different methods. Now, so I've got a bunch of R functions that I sourced to make some of this stuff easier. It got kind of messy, so I just put it in a separate file. And so remember in the original data set, when they categorized the outcome and used these weird variable selection strategies, they ended up with these variables: age, NIHSS, Bethel pre, HB, and albumin. Albumin. It's like aluminum, almost like. Bethel pre, by the way, is a categorized version of high versus low, or good versus bad. I don't remember what they call it. And that's what they did, which I disagree with their strategy. But that's what they ended up finding. And so we're going to see some similarities. So again, if we review the ones that I picked, we've got baseline, Barthel, and HB. If we look at the VSURF variables, we just got baseline, Barthel, and then Lasso is baseline, Barthel, and HB. And by the way, and I should probably say this earlier. Now, when comparing these 3, the thing that I want to know is on the training data set, I want to see what a visual looks like. I want to see how the models are differing in their predictions. And so that's what all this mess of code is trying to do, is it's trying to visually compare them. So I'm going to go ahead and generate that matrix. So that's just generating predictions for each of the models and binning it. That's not important what I'm doing there. It's just, again, to get me a visual, which is those two lines right there. And I'll put them on one line so you can see them. And so I'm going to go ahead and zoom in on this. So now we've got the two models. So let's do some comparisons. So the red is my variable selection method, and then Lasso is in green. So let's just compare those two first. Not surprisingly at all, the Lasso has a weaker regression line than the Dustin predictions. Why is that? Again, because Lasso is designed to downweight the strength of the relationship between a predictor and the outcome. And so that's exactly what should happen. That's what it's trying to do. And also both my method, at least at the end, and Lasso are using linear regression. So that's why their predictions are so similar. VSURF, on the other hand, is not using linear regression. It's using decision trees and aggregating decision trees to come up with its predictions. But, and so that's why you get it all bumpy. It's because it's not guaranteed to be a straight line. In fact, rarely, if ever, is it a straight line. But now let's look overall. So we are seeing that as the baseline increases, the follow-up increases too, and it's kind of hard to tell what's going on with HB. I could put that on the x-axis, but I'll reserve that for later. But what we do see is that the three models are generating pretty similar predictions. They're not all that different. And all three methods chose almost the same variables, except for HB, because VSURF didn't choose that. So now what the original authors did is they withheld 20% of their data as a cross-validation set, and then took the models that they fit in the original sample and then used the cross-validation set to see how well it fit the data. And so I decided to do the same thing. So I wrote my own function. That's where that's part of what's in there. It's going to use the fit from the training data set to then predict the scores on the cross-validation set. And to do so, it's going to compute a correlation coefficient between the predicted values and the observed values and output a correlation, and it's going to show a plot of those things. So if you look at my model, or my procedure, the correlation between the predicted and the observed is 0.73. So they're highly correlated, which is good, and that's a plot of it. So it seems to be that the predicted scores are really similar to the actual scores. So my version is cross-validating pretty well. Now let's look at the VSURF model. Its correlation is 0.707-ish. So it's doing pretty good. It's not doing as good as my method. And that's okay. So let's go ahead and look at the Lasso fit. And the Lasso is saying that 0.69, so it's the worst of the three in terms of correlation coefficients, but all the plots look pretty similar. So yeah, 0.6935, wow, those are the same. Oh. 0.693, 0.701. So in terms of how well they do, my model did the best in this specific data set, followed by VSURF, followed by Lasso. And I just realized I made a mistake. It's a good thing. It's always a good idea to review your code. I was saying VSURF wins. I don't know why I thought a smaller number meant better. No, it's not. VSURF loses. So I thought that was kind of cool that they all gave very similar answers. So let me just summarize. One, the way the original authors did it was terrible. They artificially categorized an outcome, came up with different variables, and they gave cross-validation accuracy statistics, but they can't be trusted because they're working with a categorized outcome variable and they're using, it's just not a good idea. And the three ways that I used all gave very, very similar results. And that may be a uniqueness of this data set. It may be that if we tried it on a different data set, we wouldn't have the same thing happen. So let me just talk about the strengths and weaknesses. So Lasso it seems to do a pretty good job. The problem and it's very efficient, it's quick, it's not as time consuming as random forest is. But the big problem is that it doesn't evaluate interactions unless you specifically model them, as well as nonlinear effects. And so if you have two variables that are interacting and you never get around to modeling that, you're never going to know that. And Lasso has no way of telling you whether you are missing an interaction. Random forest, on the other hand, will. But the problem with random forest is that it's a non-parametric procedure, and that just bothers my soul. And I've made a video about that, and I've written about that in the literature, that I just feel in my heart and in my soul that the world behaves in lawful ways. And so a non-parametric procedure like random forest is never your final destination for modeling. Instead, it's a pit stop to help you figure out what sort of parametric model to build. So VSURF is great, and random forest is great for detecting these nonlinear relationships, as well as interaction effects, but it's still, in my mind, just a pit stop. My approach kind of does the best of both worlds, and it wasn't until I started working on this video that it's still missing something. So what it does is it uses random forest and its ability to detect nonlinear effects and interaction effects, and it pairs that with visuals to come up with a parametric model. And so we are using random forest as a pit stop, and then we fit the final model. The one problem with it, now it didn't pan out in this. I was actually quite surprised to see that Lasso did more poorly than my version, because my version fit both the signal and the noise, or one would assume. So we would think that it wouldn't cross-validate well, but it actually cross-validated better than Lasso did. Kind of interesting. But I wouldn't expect that to always be the case. In fact, I would expect that to not often be the case. So it occurred to me, as I was working on this project, that it might be a good idea to combine all three of these algorithms. So we use random forest to do the initial variable selection / identify nonlinear and interaction effects. We build a regular old statistical model from there, and then we take that final model and then subject it to Lasso or ridge regression, which very similar ideas. And maybe I'll make a video about ridge regression versus Lasso and elastic net and all those sorts of things. But it would be nice to add a final step that basically takes the final model and then downweights its strength in order to cross-validate better. That sounds like something cool to do. Anyway, let me know if you think that's a good idea. I think it's a good idea. Then it's using like the best of random forest, the best of linear regression, and the best of Lasso all in one. It's like the trifecta of amazingness and variable selection. So, that's all I got to say about that. As a reminder, if you want to take classes from me, do it. That's all I got to say. Now I'm going to say more. If you want live instruction with me, I teach some live classes. So you can take classes from me either live, where you get to Zoom with me, or you get to take them on your own, at your own pace, through a Canvas course that I offer that has quizzes and discussion boards and stuff like that. So if you are interested, I will leave links in the description, including a variable selection-ish sort of workshop. It's really a data visualization / data mining workshop. And you know what? You know what? I think I'm going to add Lasso to that. Why not? Because it's a variable selection strategy. So if you want to take a class from me, please do. I'd like your money. That'd be cool. So with that, I will see you next time. Peace out. Booyah, Lasso! Lasso, lasso, lasso.
What in the hell, Bobby?
I've decided this is my space to do impressions and show them off.
What in the hell, Bobby? You threw a baseball at your mother?
Anybody ever seen King of the Hill? That doggone thing, man, they got down in there. All right, that's all I got for today. Bye.